You ever think about the invisible chemistry that kind of runs our world? All around us, there are these powerful synthetic molecules that are just absolutely essential, from medicine to industry. Well, today, we're going to dive into one of the most important families of these compounds, haloalkanes and haloarenes.
Now, you might be thinking, halo what now? But I promise you, you've benefited from them. Maybe even in the last few hours. Our own bodies make an iodine-containing hormone called thyroxine. That antibiotic that fights typhoid fever, chloramphenicol, yep, that's a halogen compound. So are anesthetics like halothane and life-saving medicines like chloroquine for malaria. I mean, they are everywhere doing incredibly important work. So what exactly are they? Well, the definition is surprisingly simple. You take a hydrocarbon, a basic molecule of carbon and hydrogen, and then you just swap out one or more of those hydrogens for a halogen atom. That's fluorine, chlorine, bromine, or iodine. And that's it. That one simple swap creates this whole new class of compounds with some really fascinating properties.
All right, to really get a grip on this, here's our plan. We've already touched on their hidden impact. Next, we'll sort them into a kind of chemical family tree. Then we'll see how chemists actually build them. After that, it's the main event, a reaction showdown between two crucial mechanisms. And finally, we'll look at their lasting legacy, the good and the bad.
Okay, let's get organized. Chemists love to classify things. And with this huge family of molecules, it all boils down to one simple question. Which specific carbon atom is the halogen attached to? So think of it like a family tree with two main branches. And it all depends on the carbon that the halogen is bonded to. In the first branch, the halogen is stuck to a carbon with only single bonds, what we call an sp3 hybridized carbon. In the second, it's bonded to a carbon that's part of a double bond or a flat aromatic ring, an sp2 carbon. And trust me, that one difference, it changes everything. Okay, let's explore that sp3 branch. First up, you've got your simple alkyl halides, which we can sort further into primary, secondary, or tertiary. Then there are allylic halides. Here, the halogen is on a carbon that's right next door to a carbon-carbon double bond. And finally, benzylic halides, where the halogen is on a carbon that's, you guessed it, right next door to an aromatic ring. It's all about who your neighbors are.
And now for the other branch, the sp2 family. The keyword here is directly. With vinylic halides, the halogen is bonded right onto one of the carbons in a double bond. And for aryl halides, or haloarenes, it's bonded directly to a carbon that's actually inside the aromatic ring itself. This direct connection gives them totally different personalities from their sp3 cousins.
Okay, so we know how to sort them, but how do chemists actually make these things in a lab? Let's check out some of the most important ways they're put together. The go-to starting material is usually an alcohol, mainly because they're so easy to get. The whole idea is to just swap the alcohol's hydroxyl, the OH group, for a halogen. And it turns out the more complex tertiary alcohols react the fastest. But here's a really clever trick. Chemists love using a reagent called thionyl chloride. Why? Because its other products are sulfur dioxide and hydrogen chloride, both gases. They just bubble away, leaving you with a nice, pure haloalkane. It's so efficient.
But what if you already have a haloalkane and you just want a different halogen? Well, there are two classic named reactions for exactly that. The Finkelstein reaction lets you swap a chlorine or bromine for an iodine, and the Swartz reaction uses a metallic fluoride to swap in a fluorine atom. It's basically like a chemical trade-in program.
All right, we know how to make them, but now we get to the real heart of it. How do they behave? When a haloalkane reacts, it usually does something called a nucleophilic substitution. But it turns out there are two different ways this can go down. So let the showdown begin. SN1 versus SN2.
So here's the big question. When a new group comes in to replace the halogen, how does that switch actually happen? Does the old one just leave first, or does the new one come in and physically push the old one out? The answer to that question defines the entire reaction.
First in the ring, we have the SN2 reaction. That 2 means bimolecular, because the speed of the reaction depends on two things, the haloalkane and whatever is attacking it. It all happens in one smooth, coordinated step. The new group attacks the carbon from the exact opposite side of the halogen, a backside attack. And as that new bond forms, the old one breaks. This causes something called an inversion of configuration, which is just like an umbrella flipping inside out in a really strong gust of wind. It's pretty cool.
Now, because the SN2 reaction needs that clear path for a backside attack, any extra clutter around the carbon atom just gets in the way. Chemists call this steric hindrance. So a simple primary haloalkane with lots of open space reacts the fastest. A big, bulky tertiary one, it's the slowest, because the attacker just can't squeeze in there. So for SN2, always remember, less clutter is way better.
Its opponent is the SN1 reaction. The one means unimolecular because the slow rate-determining step only involves one molecule. This is a totally different process. First, the halogen just leaves, all by itself. That's the slow step. And when it leaves, it forms a flat, positively charged middleman called a carbocation. Only then, in a second, super fast step, does the new group come in and attack that flat carbocation, and it can attack from either the top or the bottom.
So let's put them head to head. SN2 is one step, SN1 is two. The SN2 speed depends on both players, SN1 only on the haloalkane. And look at this, their reactivity preference is the complete opposite. SN2 likes the least crowded, primary ones, but SN1 prefers the most crowded, tertiary ones, because they form the most stable carbocation. This is a huge difference, and it leads to completely different 3D outcomes. And to get that last point, we have to talk about something called chirality. Just look at your hands. They're mirror images, right? But you can't lay one perfectly on top of the other. Well, molecules can be the exact same way. A molecule that can't be superimposed on its mirror image is called chiral. In an SN2 reaction, that umbrella flip gives you the mirror image product. But in SN1, that flat intermediate can be attacked from both sides, so you get a 50-50 mix of both handed products. And this matters a lot, especially in drug design, where the wrong hand could be useless or even dangerous.
Okay, we've seen how they're made and how they react. Let's circle back to where we started and talk about their real-world legacy, their properties, their uses, and their impact on our planet.
Take a basic physical property, like boiling point. If you keep the carbon chain the same, the boiling point goes up as you go down the periodic table, from chlorine to bromine to iodine. Why is that? It's because as the halogen atom gets bigger and heavier, those weak forces between molecules, the van der Waals forces, get stronger, making them stick together more tightly.
And check out this fascinating little detail about melting points. For benzene rings with two things attached, the para version, where they're on opposite sides, is super symmetrical. Because of that symmetry, it packs into a solid crystal really neatly, like perfect-fitting puzzle pieces. And that perfect fit means you need a lot more energy to break it apart and melt it, so it has a much higher melting point than its less tidy cousins.
But there's always a flip side, isn't there? The very same chemical stability that makes these compounds so useful also makes them incredibly persistent. They are really resistant to being broken down by things like soil bacteria, and that means they can hang around and build up in the environment for a very, very long time.
So what's the final verdict here? Are these things miracle molecules that save lives and power modern tech? Or are they dangerous environmental threats that we need to handle with extreme care? The real answer is, well, they're both. The story of haloalkanes and haloarenes is a perfect example of the two-sided nature of chemistry, and it's a story that we are definitely still writing.